Hello friends, in this video we are going to start with integration. Now what is integration? Integration is something opposite to derivative. So when I find integration of a function, actually I am taking antiderivative of that. So what do we mean by that? Suppose my y is equal to fx. Y is a function of x and its derivative I denote by f dash x. So dy by dx is f dash x, right? Then if I integrate this, if I integrate the derivative, I should get back the original function, such that if I integrate this, f dash x dx is equal to f of x. So that is what is needed, okay, as per definition. Now this sign that extend prolonged s, it is the sign of integration. Integration was basically calculus as a whole. It was invented by two people, right? One was Newton and the other was Leibniz, and both of them they invented calculus fairly at the same time and in different parts of world. And when two people think similarly, that means it really makes sense and calculus makes sense, right? So now while making his notes, this Leibniz, he used to write s because integration, what he had thought about it and the way he thought about it, it was kind of summation, okay. But then in integration we are also writing this dx, and in previous videos we have explained, it has been explained what is dx. Dx is a very small, infinitesimally small increment in x, correct? And how small? When you say infinitesimal, it is something, it is so small that you can't even imagine how small, right? And now that dx has been introduced here, then there must be some logic to that. Now before starting with actual integration and explaining this part in detail, I'll give you one simple example which I always give. You have been given a graph paper, and I'm going to draw a circle on that graph paper, right? And you have to find the area of the circle. Now what would your answer be? First of all, you'll measure the radius and just do pi r square, correct? But then that is not allowed. What is expected here is you just have the circle on the graph paper and you have to find the area. So then you would say it is quite easy, correct? What you would do is you have 1 millimeter by 1 millimeter squares on the graph paper, so you would simply count the number of squares, correct? But then if this is the circle and these are the small squares that you have, and here, I'm not going to be very accurate, but then you can simply for rough idea you can just see this. Now 1 2 3 4 5 6 and so on, there are so many complete squares. But then what do you do with squares of like this? One square like this, it is cut, this 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 is cut. What about this? They are not complete squares. So how do you account for that? Because you might get the area of this circle in terms of the complete squares. For other squares which are not complete, which are cut, okay, you have to approximate. But then what would be the solution for this? Then go for a graph paper which has got even smaller squares, let us say half millimeter by half millimeter, and then you would get more complete squares. But in that case also there will be some squares which are going to get cut, correct? So then what do I do? So I go for even smaller squares and even smaller squares, but at all the instances there still are going to be some squares which are going to get cut halfway, or you don't know, right? Even if it is cut halfway, then you can take half the area, right? But then you can't do. So the smaller the square on the graph paper, smaller the smallest square on the graph paper, you you reach towards the more correct value of the area, correct? And that is what we are doing here, correct? So that is the beauty of infinitesimally small quantities. Okay, now let us see here. I say that integration of my f dash x dx is the function itself, correct? So how do we further explain that? Suppose I have a function y is equal to x cube. Y is equal to x cubes. So what is dy by dx? Dy by dx would be 3x square. Correct. So if I use this and if I apply this over there, then I can say integration of 3x square dx would be equal to x cube, right? Now second case, I am taking y is equal to x cube plus 4, right? So dy by dx over here is equal to 3x square plus 0, so that is equal to 3x square, correct? But then, so that means, now I'll just make this line over here. So that means here now integration of this should be this. I started from this function and I got derivative as this, correct? So integral 3x square dx should be equal to x cube plus 4. But then over here I am getting x cube. Over here I am getting x cube plus 4. So what is this? There has to be some problem with the way we define this. Okay, but now again let us take one more example here. Let us say y is equal to x cube plus 48,696. Okay, and what is dy by dx now? Is equal to 3x square, but then this is constant. So derivative of constant is going to be 0, so it is going to be 0, correct? So now integration of 3x square in this case is x cube plus 48,696. So now here you must have seen that whether it is this expression or this expression or this expression, when it is integration of 3x square, the x term remains same, right? X term is same. Here it is x cube, here it is x cube plus 4, here it is x cube plus 48,696. So what does that mean? It means that if I integrate 3x square with respect to x, my correct answer would be integral 3x square dx would be equal to x cube plus c. And then this c is a constant. It can be any constant. Here the constant was 0, here the constant is 4, here the constant is 48,696. You don't know which constant. So when you integrate a function, you get the original function, you integrate the derivative, you get the original function plus c, and this c is very important. Now what is the logic behind this? What is the logic behind c? This constant can take any value, correct? Now suppose I find the value of this function. If I substitute x is equal to 4, that would be 4 square into 3, so it would be 48 plus c, correct? It is going to have indefinite number of values, correct? So this type of integration is called indefinite integral.